Okay. So here is the greatest equation of all time. Ideal gas law constant. What is so nice about this particular equation is that it does not have a V1 and a V2 or a P1 and a P2. All you need to know are your original conditions, and you can solve for an unknown variable. So you don't have to take conditions and compare them to some other conditions to solve. This is the most useful one in a lab because you don't need to compare two different situations. You can just look at your one situation and solve for it. Now, if you recall last year, there were two conditions that needed to be true in order for a gas to act ideally. And this is the same for any of the gas laws. They need to be under these conditions. If they're not under these conditions, they don't act linearly or nice and mathematical. Like what I mean by that is they're not a straight line when you start doing mathematical relationships. Okay? So let me kind of explain these two things, because we're going to hit these two things quite a bit over the next few days. Why does it have to be at low pressures? And why does it have to be at high temperatures? And it has to do with, last year we went over 6 postulates for the kinetic molecular theory. You guys remember those postulates? Probably not. Let's see if there's anyone. I don't know if I put them out of the Okay, that's one. There they are. Okay, if you flip the page to a couple of pages right before 5.8, 5.10, you can see some postulates there. Everybody see them? Those postulates are what we assume to be true for a gas that acts ideally. Okay, now notice, number one, it says particles are so small compared to the distance between them that the volume of the individual particle itself is zero. Remember when I talked yesterday about 1 mole is 22.4, and in reality it's not always 22.4, but we make the approximation because most of the atom is what? Or most of a gas particle is what? Open space. So, the idea here is that if you have it at low pressures, you've got a big enough volume. Listen very carefully here, this is important. Okay, if you have low enough pressures, you have a big enough volume that the volume of the particle itself is considered to be negligible. What I mean by that is it doesn't contribute to the overall volume very much.
Extraordinarily.
But what if I pressurize it really tightly? What do we know? What do we know? What's going to happen to volume when you pressurize something? It's going to get smaller. Okay? When you pressurize something, the volume gets smaller, and now the space between the gas particles is much smaller, that the actual particle itself is no longer negligible from a volume standpoint. Does that make sense? Emily?
That's clearly.
Okay, so I got this big volume here, right? And let's say I got one particle in this area of space, just due to gases being mostly open space. I compress it, now I've got a couple particles in that smaller space. The particle's volume itself is going to no longer be negligible.
It's just like magically distributed gas without letting out the inside.
Magically?
I'm just saying, like, theoretically, I know it's okay. It's always real well into what work, but if you could just shrink the container, you'd be forcing atom closer together. Would that increase the temperature?
Slightly, probably.
But not a lot.
It would probably be more of a pressure change than a temperature change. Yeah. But it would do it a little bit.
It wouldn't change that much.
I don't think it would do it that
None of
much.
those colliding more.
Yeah, I mean a little bit, but not significant. Okay, so I'm just introducing this now because we're going to talk about it again when we talk about the kinetic molecular theory. Low pressures allows it to have a lot of volume, and therefore the particle's volume itself is negligible, and we can assume everything occupies the same volume. Okay, so that makes it ideal to use these equations in every situation if we have low pressure. Second one, high temperatures. Which one does this contradict? Number 3, it says the particles are assumed to exert no forces on each other. They are assumed neither to attract nor repel each other. Now we know that particles attract each other and they repel each other. For example, those gases at one point were a liquid and at one point were a solid, right? Probably. But what held them as a liquid or a solid? Attractive forces between them. Okay? So yes, they are attracted to each other. The reason why they say they're not attracted to each other is because what particles do is they're moving really, really, really fast. If particles are moving really, really fast and they go by each other, do they notice an attraction for each other?
Not really.
No, not really. Okay? If you slow them down, now what happens? They will be attracted to each other. For example, we need to assume that particles moving straight line, there's no curve in their motion. Right? So if a particle goes by each other really fast, they go straight, there's no curves in their motion. But if they go slower, then they attract or they repel and they bend their motion, which changes some things. Okay? So there are 2 assumptions we're making. We're making an assumption that the volume of the particle itself is negligible. And we're making the assumption that they do not attract each other because they're at such high temperature. High temperature makes it so that their attraction for each other is negligible. Low pressure makes it so that the volume of the particles are negligible. If these are not true, the ideal gas law doesn't predict the values of these variables as well. Okay. I think you guys should remember this, but maybe not. So if I solve for R, and I put in my standard conditions for all of those variables, what's standard pressure? 760 would be right, but we're going to use 18. Standard volume. 22.4 liters for every 1 mole, right? What's standard temperature? If you take and you plug that into your calculator, I think I showed this to you last year. Why don't somebody do it?
Well, that's so bad.
You get the R, or the gas constant. Get about that. Now, I didn't do 273.15. Everybody see where we get this R constant? Could I change this atmospheres to millimeters of mercury or torr and get a different constant?
Yeah.
Could I change this to milliliters and get a different constant?
Yes.
Could I change this to Celsius and get a different constant? Yes. But how about we just remember one constant and make sure we get it in 3 seconds? Okay? Instead of memorizing a whole bunch of constants, you guys have no problem converting to atmospheres, no problem converting to liters, and no problem converting to Kelvin, right? And if I gave you grams, you would have no problem converting to moles. Okay? So, this is the one constant you need to know. But remember, when doing these, you have to have it in these units. If you do not, they will not cancel out, and you will not get the right answer. Okay? Questions so far? Let's do some math. Alright, why don't you guys do this? I don't think you'll have any issues with this. This one's an easy one. Just make sure you keep track of your units. What does it say? Adam? Oh, what's the correct? Yeah, it should be atmospheres.
And is moles.
Yep.
Oh, I was just saying you should color something. Color this and this. Yeah. Yeah. Orange, maybe?
Celsius to Kelvin, correct? Answer is? Okay. 0.57 to 2 sig figs. This is 0. 0 doesn't have any significant digits, so can't really count that. Okay? Now, just want to make sure you understand units here. Hemispheres, cancels. Liters cancels. This is on top, that's on bottom, cancels. And what is a 1 over mole? A mole. What is 1 over 2? 1 divided by half is 2. 1 divided by a fourth is 4. 1 divided by an eighth is 8. Same thing with units. Yep. Questions? Got it? Okay, next one. I do want to show you this because it might save you some time from the standpoint of not necessarily memorizing all of the gas laws. So here we look, we've got some pressure, some temperature, some volume, but then we've got a new temperature, a new pressure, and we want volume. That sounds like a combined gas law. But let me show how you can figure this out. Okay, do they tell you anything in here about moles? They don't, do they? So let's go PV equals nRT. Let's take our variables that we know stuff for and solve for them. We know P, we know V, we know T, right? Divide by T. That's a constant and that's a constant, right? Two constants multiplied by each other will still be a constant, correct? Do you see the combined gas law now? If P times V divided by T gives you a constant, couldn't you set P1 V1 divided by T1 to equal P2 V2 divided by T2? Are you seeing it? You can do this for anything. If you only had pressure and volume, these were your two changing variables, and these were constants. Replace this with K. What do you have? Whose law? Boyle's law. And you can do this with any of the laws. Just identify what variables you have changing, get them to one side, and your other side should be all your constants. Okay? So whether or not you find that useful, I don't know. I think it's pretty cool. Okay, so we got P1, what is it? 345. We got V1, what do we got? 3.48. Is it getting hot in here? No. Holy cow. T1, is it in Kelvin? I can't, nope, can I get in Kelvin? You guys do it? 258. Right, P2, T2. Okay, we want to know volume. They gave us pressure and they gave us temperature. 468. And what is the temperature written in Kelvin? 309. You guys can use the ideal gas law and solve this then. Not the ideal, sorry, the combined gas law. Couldn't you, Isaiah?
Oh,
When did you come last year? Well, about what time?
November 6th. So yes, I remember this.
You do remember this.
Do I remember or do I know we did it?
Well, you know you did it. You don't remember because you never did your homework last year, so.
And I did fine. See? I lived another
Yeah,
day.
you did fine. C. That's what you got. A
I'm pretty sure I got a B.
C. But you could have gotten a.
A.
You're trying like A. Volume is 3.07.
Yeah.
Yeah? Okay. How much time we got? Hey, 9 minutes still? So hopefully that's right.
We need a short word.
What do you guys like, especially stuff that's reviewed, do you guys like just me letting you do it? Or would you prefer me showing everything? What is your preference?
Depends on how much I remember.
Yeah.
Sure. Sure. Well, okay, I mean, yeah.
I let like if you do one and then you let us do one.
Okay, well, this next one's gonna be very, very similar. Let's just look big picture. You can kind of look big picture here. First, it says change in volume. That's something, maybe not something you're familiar with. Emily is. What does change mean? Okay, so the final volume minus the initial volume. So what we're gonna have to do here is probably do the ideal gas law twice under different conditions. They give us a mole amount, they give us temperature and pressure. Then they say it's heated to a different temperature and a different pressure. Now, does the amount of particles change? No. So that will be the same N for both. So I can say N for both is 0.35. I got a T1 and a P1. And we're solving for V1. Or V initial, you could say. How about that? First conditions would be your initial conditions. Does that make sense?
It's not.
Then you would have a C2 and a P2 that would give you the final. Did you plug in those variables and solve two different ideal gas law problems? You guys good with that? Riley, you hear that?
Yeah.
Okay. And once you got two different volumes, what would you finish with?
Subtract the final volume.
You guys see what your grade was?
Yeah, oh yeah,
Shout out to
99.
me for this.
Yeah.
I only got you like a fourth of a point, right?
Yeah.
You just wrote it wrong.
Wait, Isaiah, you got a 99?
We got a 99.
Like that?
Yeah.
They
Good.
did really well. The only thing they got wrong was they wrote the wrong number down
Instead of
wrong.
3.17, we wrote 3.7.
Did you guys, did they get the best score?
They tied for the best score.
Who else got it?
Emma, we could have gotten the best score.
Someone else wrong, so I'm not too stressed out. I can't do it.
Okay, I'll try.
I'm probably not gonna have points. It's a soccer ball.
We don't have to put our work on this, right?
Maybe.
Like on the actual paper.
Well, I'd love for you to put your work on
I feel like it would make it messy.
it. Well, what I would do, you could either put your work in here or.
That is not a soccer
It's like a
ball.
league pad.
That is so weird.
You put your work.
What is that?
It's a soccer ball.
That's so cringe.
Okay.
And then what I'm gonna do is I'm gonna like compress this down to a smaller piece and like stick it out somewhere.
Yeah, that's why I like that whole space.
Yeah, but it won't need to be that big. I'll make the font smaller. I just made a bigger sheet.
Should we write all our like variable guys?
Variable guys, what is
Well, I can show you what like Cole started doing with his group, which is kind of what I want.
Oh, wow, Cole is the basis of the entire event?
Well, this is the same thing that I had for other years. So you can kind of see, like he wrote some of his work. So there's your X's and your Y's.
Yeah, that's what I was thinking.
Yeah. You don't have to go crazy. Like you don't have to show every little step.
This is pretty good.
That's like
angle.
Also, if you want us to go like X1, X2, X3, X4, X5.
That would be, I mean, yeah, even if an X is 0, just say X2 is 0. Does that make sense?
Yeah.
So you should have as many X's as Y's.
Yes.
Alright, what's your change volume? Should get
There's a Y component.
Yeah, there's Y's
I
over
only
there.
had 3
Oh, so
questions.
you want us to add all of these?
It should be around 3.
X1, X2, X3, X4.
What'd you get for B1?
X7,
X8,
.014.
Y1,
Did you convert to Kelvin?
Y4, Y5, Y6.
Why is 0 there? Is it gonna go up?
I had 8.
Ah, yep, there's your problem. Storing needs to be in atmospheres.
Every
I
measure.
did that.
Okay.
What is
But I had my final smaller than my initial.
That's fine. The difference is just negative,
That's,
Okay.
Y5, Y6, Y7.
right? Doesn't it come up to be like a -3 or something like that?
Yeah, it's negative 2.98839.
Yeah, approximately -3.
Because I don't round in the middle. I just
No,
like
it's not.
That's what you should do.
It's fun.
It's
It's fun to make it all in one. You do very
So I'm guessing, I don't know if it was Ben or Ben that asked me that question, but I'm guessing all you need to do is get 4, correct, into atmospheres, and you would have.
well, yeah, but you're only doing.
So what would you do like? How would you write that?
How would I write what?
3 times smaller?
No, I would just say it decreased 3 liters. So the answer
Oh,
is
okay.
Okay, I do want to go over this one because this is one that is a little bit different. Okay, it says suppose you got 2 200-liter tanks. They're filled separately with helium and hydrogen. What mass of each gas is needed to produce a pressure of 135 atmospheres and at a temperature of 24 degrees?
Solve for mold and refer to that.
Yep. You solve for moles. You should have the same moles of each, right? Because we talked about how if you've got a certain volume, the moles should be identical, right? So you're going to solve for moles. Once you have the moles of each, you would then convert to what? What does it want you to finish with? Mass. So that was just using molar mass, right? So here's your mole. Here's how you would solve for moles. Okay, your pressure is 135. It's in atmospheres, so we're good. That is a whole load of pressure. Holy cow. 135 times atmospheric pressure.
That would correct your person?
200 liters. 0.0821 and 297 Kelvin. When you do that, you should get a mole number approximately 1.11 times 10 to the third.
Really a lot of fun.
And that would be, this would be this many moles of helium, and then that many moles of hydrogen. You guys understand, it's in a 200-liter, it wants to know to fill a 200-liter volume. So both would have the same number of moles because we're assuming that we're at a, well, this actually probably wouldn't work with the ideal gas law because it's at an excruciatingly high pressure, isn't it? This kind of doesn't follow ideal conditions. But we're still using it as approximation. I'm guessing these would not be the same under extreme pressure like that. But we're going to assume everything's an ideal situation. So then you finish with what?
Well, wouldn't it be H2? Wouldn't it be H2?
Oh,
Yeah, I know.
What?
No, 1, 2, 3.
2.02. 4.0.
Because that's my.
He's at the 4.3 now.
I know. There's no explanation.
Where'd you get X?
Yeah, I'm gonna like this street, but.
Hydrogen should be 2.24 times 10 to the third.
It's just 0. No, this one's not.
And 4.4.
That one is my.
Any questions so far? Was this overly complicated? Did you feel it was okay?